Merci d'être venus si nombreux. We have the pleasure today to have with us Mr. Sarkisian. Mr. Sarkisian is a leading director of SOM, Skidmore, Wells & Merrill architecture and engineering firm in the United States, but he's specialized in, he's based in San Francisco, specialized in structural and seismic engineering. So we're going to see things we don't speak very much here about seismic and earthquakes design. So it's good. Maybe you have to begin by the beginning. We don't have so many earthquakes here. Yeah, we just had one, yeah, last week, but a small one. As he is in San Francisco, as you may know, San Francisco is on la faille de Saint-Andrea. Donc, so they are they have to work on that, and it's a very hard point for designing tall buildings. Mr. Sarkisian is a structural and seismic engineer, partner of SOM, and he received a Bachelor of Science degree at the University of Connecticut, then a master's degree at Lehigh, Lehigh University, and also an honorary Doctor of Science degree from Clarkson University. His work is focused on solutions for projects of high level of seismicity, and he's been working on towers. Especially, we have 3 references here, but he may know he have been working on 100 projects, maybe more. SOM is a large firm. The U.S. Embassy in Beijing, the NBC Tower in Chicago. Are you going to talk about that? No. The Cathedral of Christ the Light in Oakland, no more? Ah, the Jinmao Tower. The Jinmao Tower is the tower in Shanghai called Louvre-Bouteille. That's the one? The Jin Tower is that one? Is that the one like with that? The first one. No, because we used to call that the opener. So it's not that one. The Al-Amra Tower in Kuwait. And he also has developed patents for high-performance seismical and structural engineering. He's giving classes all over the world, especially in France and in French. So today he will speak French with us. But can you speak some French? You'll do that in French. I'm trying to speak English. And especially at Berkeley, Stanford, and Cole Poly. He has been honored for many prizes and over seismical and earthquake engineering, and he's working on the International Association for Life Cycle Civil Engineering. As I was last weekend with his friend Mr. Becker in New York, they are both developing. They are very impressive in the way they are developing methodology for earthquake, but also for designing projects. Not only calculating them, but designing them. Skidmore, Wells & Merrill is, for us, an impersonal society, but in reality, it's a personal one. We have those engineers, and happy to have the honor to be with you today, to have you today here. But they have a long affiliation of great designers. And maybe you're going to speak about that today. So let's, vous pouvez applaudir Monsieur Sarkisian.
Thank you, Mark. Thanks, everyone, for being here. I'd like to talk about cities today and the relationship of buildings and the ground. And I'd like you to think about whether our structures are meant to be permanent or temporary. And what about our cities and how we think about our cities and the design of our cities, and how do people react with our buildings? And when those buildings aren't super tall, can we create environments that are interesting and places where people can share ideas? A few years ago in Amsterdam, there was an experiment that was done, and a group of people wore a tracking device over a period of about a month or so. And you could interact with this experiment by watching the paths of people. And the paths of people are what you would have expected. The paths that they took were paths on sidewalks and roadways. So, a question. Are our cities ordered by the streets that manage flows of vehicular and pedestrian movements, where the areas in between are void and absent of life? Should our structures be restricted to regular load paths, defined by elements set up on disciplined grids, ignoring the spaces between, ignoring their contributions only because an order has been imposed upon us? Should our structures be designed as static objects or as objects that are in continuous motion? Should we continue to think of our structures two-dimensionally instead of volumetrically? Now, you can argue that this might be a natural occurrence, but I would argue that man has a lot to do with the change in temperature on the planet. Over the last century, it was about a degree and a half Fahrenheit change, and we expect that during the 21st century for that change to be about 2 degrees. The impacts are clear. The impacts on the environment, the impacts on frozen land are all a result of this change. So this change has brought on places like this. This is one of 2 places on the planet where every seed known to man is stored. And that's just in case. Just in case the change that happens puts us in a situation where we can't go back. So the question for us is, how do we have an impact on this potential change? When we build buildings, most major buildings, it takes 20 years for the carbon associated with operations of buildings to equal the carbon that's emitted at the time that we build buildings. So if those buildings come out of service at any time along the way, we've put more carbon into our buildings the day we build them, and the operation becomes even more insignificant. So how can we think of ways of overcoming this change? A few years ago, we had a student who was an intern with us, and we had an architect in our office that was interested in bamboo. So I said to this intern, I said, there's something about bamboo that's unique, that's different, and we should research this. So he went over to UC Berkeley's library, and if you look at bamboo, it's got a series of lines along the height of the culm. And if you look carefully, the spacing of those lines is different along the length. It's closer near the bottom. It opens near the mid-height. And then if you saw the top of these, they'd close again. The lines represent diaphragms. The bamboo is hollow. The diaphragms support the walls and keep them from buckling. So when the wind blows, the forces on one side becomes higher in compression, and those diaphragms are there to resist the buckling of the walls. The spacing isn't random. The spacing is mathematically predictable. So the equation that you see here is a quadratic equation that you can use to define the spacing of the diaphragms. The spacing of the diaphragms, the diameter of the culm, and the thickness of the wall is all mathematically predictable. And if you were to plot the relationship of the spacing, the relationship of the diameter of the walls of the bamboo, or the thickness of the walls of the bamboo, you get an equation that looks like this. It's the bending moment diagram of a fixed base cantilever subjected to a constant horizontal load. It's the same principle. The spacing, the diameter, and the wall thickness are all related to the same mathematical principles as the fixed base cantilever. So we looked at this idea, and we looked at applying this idea to a structure. And perhaps diaphragms are now outrigger trusses. They're connections between the core and the outside that aren't even. Perhaps they're closer at the bottom. They open as we get to the mid-height, and then they close again. We found that with this type of spacing to connect the inside and the outside, we could save about 20% of the material in the lateral system because that interconnection was so efficient. The core varying in the form that you see here in the middle, the perimeter connected to that core to form an overall system that was combined with these heavy diaphragms. The spacing and behavior is in other places. It's in the tail of the dragonfly and other insects where, again, the section is hollow. The rings are there for a purpose, to keep the walls from buckling. And the rings or the diaphragms vary in spacing but are mathematically predictable. It's been a few years now, and Mark mentioned this project. This is the Jinmao building in Shanghai. It's 420 meters tall. It uses concrete and steel and a combination of concrete and steel to form the structure. And the most important thing about this building is that it links the center to the outside through a series of outrigger trusses that happen only in 3 places along the height of the tower. We found that those links were very important to control displacement in wind and seismic events. And we found that you only needed 8 of these in the floor plan for each of these levels, connecting the central core, which is reinforced concrete, and these composite columns at the outside. That's it. But we also found that if we built those trusses at the time of construction, from bottom to top, the creep and the shrinkage and elastic shortening of the center relative to the outside was large enough, and those trusses were big enough that it would literally tear them apart just under its own weight and the relative displacement between the materials. So material is so important for us to consider in these tall buildings, and the relative displacement is so important. But probably more importantly was how we controlled the behavior. And then what we did is we introduced pins into the structure to allow it to move like a mechanism, a free-moving mechanism during construction. No bolts were placed. No bolts were placed in the initial erection sequence. So allowing the truss to move, and the most important part of it were the slots at the head of the diagonals. So it's been a couple of years, but this is what I did on Saturday nights. Okay, there's a beer bottle in the back. It's my daughter, who's now just finished graduate school. This is a popsicle stick model that we created with tongue depressors and wood dowels to create this and confirm that the relative movement worked, that the thing would slide. So the working drawing, the structure, the truss at the plant, then in place, and to give you a sense of scale, that's one of the connections for one of the members in the truss. So it started with a problem where we needed to allow for relative movement. And it ended with this idea that perhaps structures should remain in motion, or we should think of structures in motions at times during their lives. So there it is. It's finished. Now there are 2 other, one of which Mark talked about, which is on the left side of Jinmao from this perspective, and on the other side is the Shanghai Tower, which is just finishing. And actually Jinmao is the shortest of all 3. At about the same time, I went to this place, and this is called the Isle of Chiloé, and it's very, very far south. It's about an hour-and-a-half flight south of Santiago. And what I found there was indigenous architecture, a place where buildings were of low scale, but I also found that there were a number of Jesuit churches. And these Jesuit churches did very well during the 1960 earthquake. In fact, it was probably the largest earthquake ever recorded until recently. And I began to wonder, why did these churches work so well in the earthquake? So I climbed up inside of the attic of this church. And what I found was all of the connections were done with wood dowels. Wood dowels that fixed joints when they needed to be fixed. So you can imagine during a wind event, maybe a frequent seismic event, joints wouldn't move. But during the big earthquake, the joints would rotate. The friction would be overcome and the joints would actually move. So I was convinced that because these wood dowels were used in these churches, they performed very, very well in the earthquake. No mechanical fasteners, no nails, no screws, just wood dowels. So you wonder about the behavior of structures and what the wood dowel might mean to our buildings. And maybe we have buildings that use joints like this, that look more like your shoulder or your hip, where you have a center pin, again, the pin that comes from Jin Mao, the idea of the pin allowing movement, in this case allowing rotation about a point, the curved plate attached with a friction connection where you have a friction surface that can slide, bolts that are in long slotted holes. So as the joint gets very high bending moment, it eventually will start to rotate and they'll dissipate energy, all right? And when that energy gets dissipated, it's much like what we do in our buildings today. We damage our structures to dissipate the energy. In this case, we're doing it elastically, and we're doing it through friction. So the idea is protect our structures so that later we don't have to repair or replace them after an earthquake, again with the idea that we're trying to protect the environment. So that's the ultimate goal, to make the building safe but also perform very well. So in the future, perhaps our buildings will have joints that look like this rather than fixed joints that we typically use in steel buildings that are fully welded together. A few years ago, we were asked to do this building, and on the surface, it seems like a pretty regular building. It's an office building in Beijing. The client asked us if we could create a window that allowed the world to look in and people that were inside to look out. And our goal was to create the absolute most minimal structure. So this is a cable net wall. In fact, I believe it's still the largest cable net in the world. It's 90 meters tall and 60 meters across. And we found that the movement under wind loads were so high that we needed to break the span of the glass wall. And the way we did that was introducing these two diagonals into the building. When we introduced the diagonals into the building to allow for the restriction of movement of the glass, we found that they acted like braces, huge braces that you might see in a braced frame of a building. And we found that the forces that were attracted in these braces were so high that you couldn't design the cable to take the load. So you make the cable bigger because the force is there. As soon as you make it bigger, it attracts more force. Okay, and you keep tracking, and you find a way, finally you find that you just can't design for it. So this joint above this museum, which was inserted into this wall, became the critical part and the consideration for us in design. So we thought of the pulley. The idea that if you had a pulley, you could move the building back and forth, and there'd be very little, if no additional force from the earthquake in these diagonal members. Now, because the cables were so big, the diameter of that pulley needed to be about 7 meters. So our architects said, no, there's no way we're going to have a pulley that's, nominally 20 to 22 feet in diameter at the face of the building, so we have to figure out another way to do it. So what we did is we created this, we call it a reverse pulley or a rocker. And here comes the pins again. So 1 pin, 2 pin, 3 pins, and actually there's a 4th pin. And what that does is it allows this frame to move without additional force in the cables by the use of primarily these 3 pins. And you'll notice that it's not symmetrical because the wall, the center point, the support point in the wall is not symmetrical. And if we didn't see any elongation in the springs, which we didn't, then you find that your experiment works. So the pulley works. When you move that frame side to side, and this actually is in our office in San Francisco, you'll find that in fact it does work. So that pulley with those pins became this mechanism, which allows for the support of the glass wall and also allows it to move in an earthquake. So those big forces wouldn't be attracted. So just to get a sense of scale, here's the men that are cleaning the windows, and you get a sense of the height of this cable net wall. A few years ago, we had an opportunity in Oakland, California to design a cathedral. And the cathedral is based on mathematical growth patterns and also some patterns that you see at a large scale. It's based on the Vesica Pisces. And essentially what it is it's 2 spheres that are interconnected together and truncated on each end, and on the outside of the building it's a cone. So the idea was to try to use the most honest materials possible: wood, concrete, steel, glass. And it's a place where we have very, very high seismicity. So we've got very, very strong ground motions. We're within about 5 kilometers of the Hayward Fault. So we used bearings underneath the cathedral itself to decouple the superstructure from the base. And to do that, it allowed us to use these materials that otherwise would be quite fragile, right? Non-ductile. So wood is a very good material, but as soon as it starts to bend, its flexural strength gets to the point all of a sudden it'll just fracture, right? So glass obviously is the same way. It's a fragile material. So this seismic isolation helped us control movements of the superstructure itself so that we could use these materials in an efficient way. Everything that you see works for the building. So the louvers at the perimeter form the shell, and you can see that the louver size and orientation changes over the height. So at the very bottom where the shear is the highest, the louvers are fairly tall and they're very vertical. When you get to the top of the sanctuary, the louvers are small and fairly flat. And what this also did is allowed light to come into the space in a very beautiful way. So the Cathedral of Christ the Light is the name of this, but I think the principle here, the idea here is that this building could be subjected to very strong motion. And we use these bearings to control the behavior of the building and allow us to use these materials. What you see is an image of Christ, and it's not projected. It's made up of 90,000 holes that are digitally mapped, that are mapped through aluminum panels. So what you're seeing is the light from beyond. And the image changes during the day, and sometimes it disappears. But it also allowed us to create this type of piece, this type of artwork, because of the way we control the ground motions at the base and the use of these very lightweight panels. So it's an idea that uses wood. It's an idea that uses these bearings to come up with a solution that we think is pretty successful. A few years ago, I was at this place, and I'm sure everybody knows this place. I was here with my daughter. I have 3 girls, and before each of the girls started college, I took the girls on a trip. And this is my middle daughter, and we were here about 5 or 6 years ago. And we walked into the plaza at the Eiffel Tower, and a lot of people were congregated. And I said to my daughter, I said, the way you see this building is you walk it. You walk the stairs. So we entered the side here where there are no people. And we went up to the first platform, and we looked down. And this is what we saw. People in line for the elevator. They're in line, and guess what? They're forming the golden spiral. Naturally. This is the least energy of people in line for the elevator. Okay? So you wonder, right? You wonder, is this random, or is this what really happens? Was this really a natural phenomenon that's happening? And it happens in other places, in plant growth, in shells. This is a competition that we submitted for and lost. This is for the Transbay Tower in San Francisco. Cesar Pelli and the development team that he was working with has won the project. In fact, this building is under construction. So a huge disappointment. But what happened during this time, during this competition, is probably more important than the building itself. We started to look at how can we take natural forms and think of them in structures. Now, when you see a hurricane, let's say you're watching, I guess we don't get hurricanes. We don't get hurricanes here at all, right? No. Okay. So I grew up in Connecticut. I grew up in Connecticut on the east coast of the United States, just north of New York City. And when I was a boy, it was very rare that hurricanes would come to Connecticut, right? My father said, here's what's going to happen. He said, when the storm comes, it will build up. It's going to get very, very strong over a period of time. And then it's going to get really strong, really, really super strong. And almost momentarily, the winds will die down. It will, and they will stop, and the sky will become clear. And then after a few minutes, as the sky is clear and there is absolutely no winds, all of a sudden that storm is going to come, not incrementally growing, but just there's going to be a surge of winds. And then it'll incrementally change. And I remember the windows blew in. I mean, it was a mess, and it was the only time I think that we ever had a hurricane that came and hit the coast of Connecticut. So I started to think about the hurricane. I was thinking about it as a kid, but I also started to think about it during the time that we were looking at this project. So the hurricane is something that we usually see and plan. We usually see it on the news. It's a typhoon. It's not hitting here, but it's hitting other places around the world. And you can see that it's in the form of the golden spiral. And the reason why the forces are so high is that in the very, very center, not in the eye of the storm, but on the edge of the eye of the storm is the highest force. And as you get toward the edge, it gets less and less. But you can mathematically predict the shape, right? So what if you took the hurricane and instead of it as an applied force, think of it as a resisting force, equal and opposite. Okay, imagine that. So imagine structure near the eye being strongest and least at the edges. And imagine standing the hurricane vertically or perhaps three-dimensionally. So you get a resisting system now that's thought of in a different plane. And then combine the idea with something that has been around for a long time. And Mitchell came up with the idea mathematically describing the perfect cantilever with 2 points of support and a single point of force. This is the shape that the cantilever actually, its most efficient form would be. So what to do? This mathematical prediction. At the same time, a friend of mine became very interested in the idea that we were developing for the tower, and this is an excerpt of what he said during an address to his incoming students for that year. He was the head of the San Francisco Theological Seminary, which was located in my hometown in San Anselmo, California. And he said at the time, he said, what if we could develop strong, flexible, responsive, adapted, sustainable human beings based on the intrinsic architecture of the hurricane? Buildings that exist in harmony with, instead of trying to resist and stand up against and conquer the powerful creative forces that might otherwise threaten and endanger us. So in other words, coexisting, right? So how can we come up with ideas that coexist with forces rather than just resist? So we took this idea, and the proposal that I had was a building that looked like this. Of course, it doesn't work. Our architects didn't. No. There's no way, right? Can you imagine that on the skyline of San Francisco? Okay, so imperfection. The idea that this principle could be applied to something that had a varying form. So over the height of the building, we saw areas of highest demand at the base. We wanted to open the central axis to this train station beyond. And what you see is you see a beautiful resolution of structure that starts out highly concentrated and then opens as it gets towards the top. It's a proposal. As I mentioned, we lost the competition. But nonetheless, it's something that I think leads to other ideas. There's a theory called emergence. Now, emergence isn't something that's absolutely new, but it perhaps sets forth a way of thinking that we might consider with our buildings. And emergence is the idea that the collective of common individual elements when working together are far more powerful than any individual element working on its own. All right? So there are examples of that. Birds in flight, sand that's impacted by winds, termite mounds that are super cooled, honeycombs built by bees, and guess what? Cities, people, this room. This is an example of emergence. The idea that the collective, when sharing ideas and working together, are far more powerful than individuals on their own. And there are boundary conditions, okay? Boundary conditions like, going to parties or sleeping or, these things impact how this reaction happens, right? But it's a very powerful way of developing ideas. So what is it about the collective that creates this energy, this efficiency of ideas and productivity that impacts our buildings? The idea of a magnetic field, when we put iron filings in that field, is basically an indication of where the least energy is for those material pieces to be. We can't see the field, but we use the iron filings to help us see the field. But it's that arrangement that perhaps we need to think about in our buildings. So in our buildings, we think about boundary conditions like points of support, right? Column positions, perhaps, at the base, but without drawing a column line, putting a point of support and putting a unit load at the top. The red being areas of highest demand, the blue least demand. And interpreting this structure into something that perhaps is something we haven't seen before. And maybe we need to think about our structures more as surfaces or volumes rather than beams and columns to create something that perhaps is beautiful and perhaps something that leads to even future efficiencies. And you can use this kind of principle, these optimization principles, for forms that are not tall buildings, right? Buildings that have shapes that are less defined, perhaps. Points of support, in this case, an analysis that looks at gravity loads. And the diagram that you see on the far right is, again, areas of highest concentration of load, and blue with the red and blue being least concentration. And you see these sort of organic trusses that start to form, providing the most efficient way for those forces to flow. And thinking about structure perhaps through spaces rather than just at the perimeter of spaces. How many of us think about this space that we're in and the three-dimensional volume of this space and perhaps structure that moves through this space in some way that we haven't thought of before? This is the least amount, it's working toward the least amount of material for these points of support at the base, and you see the response of the positioning of material within the structure. The strongest remains, right? It's the idea, in this case, winds against the Matterhorn. What's left over is perhaps what we should focus on in terms of our buildings. So buildings might look like this, where the structure erodes over its height. It's an apartment building in China that we've proposed. It's not built yet. But what happens is it creates these very interesting spaces that are far above the ground, but perhaps the structure is eroded in a way, in this case maybe using concrete walls and so forth, over the height of the building that relates to architecture and creates something that might perhaps be unique. Now you can take this kind of idea, those principles, and I'll say apply them to things that are pretty regular, right? This is a pretty regular looking office building in Salt Lake City. We've got a little problem. Cesar Pelli actually was involved with this project here. There's an air rights problem at the base of the building. So this is a performing arts center, and somehow the ownership rights are shared here, but no vertical structure can pass down through the volume of the performing arts. Now, Salt Lake City is kind of it's not a super urban, super dense place, right? So you wonder, how do we get ourselves into these this sort of problems? Why would we have a performing arts center that spills over into the neighboring site? Anybody's guess, I don't know. It has to do, I'm sure, with the size of this particular site for the Performing Arts Center and the fact that the program exceeded really what they needed for the site. So, here's our 25-story, very regular office building, not able to meet the ground on one side. And if you look at it in plan, it's pretty straightforward. I mean, this is a building that you might do anywhere in the world, where you have a center core, it's concrete, a steel frame at the perimeter. But guess what? You can't have anything here for the lower 5 stories of the building. So what we did is we looked at this structure as if it was an optimized volume. And what you find is something really quite interesting and beautiful, where the areas where we have to take away structure, you find that the points of support, there's a concentration of load. And again, the areas in blue are not high demand. The red is the highest demand. But this is a pretty wide building, right? So you'd have to step these tree-type shapes across the width of the building. And the tree shapes don't work so well with office use, right? So what to do, right? We've got this nice study. But we found also when we looked at this study that the building tends to turn over, right? It makes sense because it's highly eccentric and it's actually leaning under its own weight. So instead, we took away all the columns at the bottom, all of them. And we sent the core up for 25 stories, and we suspended the entire perimeter of the building with a truss system at the top. And these are all columns in tension. We built it from the bottom up. We had a special system to do that. And then once we reached the top, we placed the truss, we pulled the temporary shores away, and this entire building is supported by the central core. The bearings come back. The pins and the bearings are repeating themselves. Now, this isn't a base isolation where you put bearings on the bottom, you put them on the top. And you might ask, well, why did you put them on the top? We put them on the top because we were trying to take load from those big trusses and send it vertically through the core. We didn't want those trusses to bend the top of the core. So using these bearings, we actually forced most of the reaction to go straight down into the core and pre-compress the core, you might think of. So we do have large earthquakes, so we have overturning, but all of this weight being on the core actually helps us for overturning during the seismic event. And then we have things like these shear keys that keep the truss in place so it doesn't just freely move at the top of the building. So this has really happened, and we actually created a saddle system on one face of the building to temporarily support it. We used the core like a very large mast during construction to do that. And this is just a few weeks ago. This is a beautiful place, mountains beyond, this truss system being placed at the top. But the idea came from that optimized system where we were looking at that central core and also the way those loads would flow. So this was the night before we actually released the temporary system at the base of the building. And one thing to note that because of the construction sequence, we actually had the exterior wall being placed on this building before we released the jacks and having the building come down, which is a very difficult thing to do in terms of controlling movements and so forth. Okay, so back to nature. You know, we've looked at these sort of optimization studies for tall buildings, and in these studies you find that the bracing systems for our tall buildings, in fact, are more efficient if the bracing's not concentric. Okay, so you think about the John Hancock building in Chicago or other buildings that here in Europe using concentric braced systems, right? Well, you find that if the bracing system, in fact, was a geometry where it's approximately 3/4 to 1/4 in height, the system is much more efficient in terms of resisting lateral loads. And there's an interpretation, okay? So architecture can be pretty static. If we were to design that building the way I showed you before, it's a pretty sterile, pretty static kind of idea. But what we did on this project in Shenzhen, and it's a building that's under construction, is that we took the original concept and we interpreted it. First with a regular spacing over the height, and then next varying the spacing over the height. So the density at the bottom is sort of like Trans Bay, the one I showed you from San Francisco. But what it does is it allows for greater open space, column-free space at the top of the building, and a response that I think is far, far, far better than it would be with the sort of theoretical solution. So here are the principles, and it's based on virtual work. It's based on the application of lateral load and the placing of these bracing members that give us this very efficient response. Now, for tall buildings, and we had a small earthquake here just a week or so ago, but for tall buildings, the greatest dilemma has been that for a tall structure, the best solution is to create members that are in tension or compression. Okay, bending is very bad in tall buildings, right? So moment frames in a tall building, bad. Not that it doesn't work, it's just that it's very inefficient, right? But if you could create structures that had diagonal members, that's good, tension and compression. But the problem is when the earthquake comes, tension and compression could become very brittle, right? So what we've done is we've created these links or these fuses that allow the building to fuse and dissipate energy during the big earthquake. So it's very stiff, I'll say, for typical wind conditions and moderate earthquakes, but when the big earthquake comes, these links will fuse and dissipate energy, sort of like that pin joint that I showed you earlier. So we think this is a breakthrough in terms of how we combine systems in very tall buildings and how we're able to get efficient structures and deal with the earthquake at the same time. So this building has that. There's a fused system up the height of the building. It happens on both towers. It's on the sides of this one. You can't see it. But combining and thinking of both loading cases, primary loading cases in design. Really large open spaces at the bottom, no columns, just structure at the corner. Again, reflecting on Trans Bay, which was probably 10 or so years before. So architecture might look different. I mean, the building on the left is probably one of the most important tall buildings in the world, done in the late 60s, where we combine a bracing system with vertical elements and create a very, very efficient response. And the building on the right, which is under construction, that uses the same principles but perhaps thinks of structure in a different way, in a less conventional way, but provides savings and lessens the impact on raw materials and also materials that eventually have impact on the environment. Now you can take this and you could think of it on the horizontal too, okay? So these aren't just principles for tall buildings. These are principles that you can use in bridges. Now, forever and ever and ever, we've got bridges, Warren trusses and Pratt trusses, and trusses that are very efficient, that we just think are just they're good enough. We just keep using them, right? I mean, you see them everywhere. Now, there's some creative engineers. We've got a couple of creative engineers here in the room that rethink this and do beautiful, really beautiful responses that are not so conventional. But if you take this, and this is Los Angeles, this is at the airport, pedestrian bridges that are up to about 160 feet long. And you take the principle of the tall building and you turn it on its side, where you have the fixed base of the tower now in the middle, okay, and you mirror it. And you look at the bracing, the diagonalization, not as a conventional Warren truss or Pratt truss, but as something that looks more at this 3/4, 1/4 principle, and you find that you can save 20% or so of the material by doing this. Now you could argue, oh, this is harder to build, right? This is not what people normally do. All right, that's the first thing you're going to hear. But the point is that these opportunities are there, and I think we're getting better and better about the communication of our design drawings to construction. So these things are going to become, I think, less expensive to build, and in the end are the right things to do. Savings of material, perhaps prefabrication, these are all part of the idea. And you can use these optimization principles along the length. In this case, it's a cylindrical section that shows the placement of these trusses and then the interpretation of these trusses when we look at it three-dimensionally, right? So it's not something that necessarily has to be in a plane. It can be around the shape. Now take this idea and put it in plan. And Mark Hymans is here. Mark worked in our studio in San Francisco. And he's very interested in post-tension systems for buildings, right? And we were building this building, which is an office building in San Francisco. It's I'll call it a core-only building. So it's all concrete. And here it is. Here's the core. And it's got a series of columns around the perimeter. That's it. So this is something we build over and over and over again. But what if we took these same principles and looked at it in plan, mapping the stresses in plan and mapping the placement of post-tensioning and materials, and also creating flat plates that you look at things like deflection, long-term creep and shrinkage, so that you can camber in advance and look at it carefully. So the spans here are about 14 meters from the core to the outside. They're pretty far, and normally we would use what? Beams, we use maybe steel, but in this case, the idea was to use a flat, just a pure flat plate. Now, when you think about the environment, you think about these kinds of things too, not just a flat plate, but maybe putting things in the slab, right? So, okay, so these guys, well, a lot of people have these. When we drink these water from these water bottles, we usually put the caps on them, right? We usually take them and put the caps on, and then we say, we'll put them in the recycling bin. Okay, probably 80% of these things can't be recycled. They just go into the landfill. We started thinking, you know, what about this landfill that we've got, and what about what happens inside of this container when you put the cap back on it? It traps the air, right? Most of our slabs in our buildings, when you get out, for instance, if you had a two-way slab where you had 4 columns, most of the concrete in the middle you don't need. And the only reason why we put the concrete there, because it's easy, right? We just pour the floor, we put the concrete in. In fact, the concrete in the middle is actually adding mass, and it's using raw material. It's creating carbon. But if we put these water bottles into the slab, now I'm not saying just throw the water bottles in, okay? You gotta place them in an engineered way. You gotta get concrete in between them, and you've got to place them so you have concrete on the top and on the bottom. But it's a volume that you can take away material and use this stuff that's going to end up in the landfill anyway, right? So think about these things when we talk about the environment, and it doesn't have to be water bottles. It can be compressed plastic, right? There are other ideas out there. There are spherical balls people have put in, and you know, all that stuff works. But the point is, can we use material that's going to be in the landfill anyway into our structures, lighten the mass, in our case in San Francisco, because we have high seismicity, it gets into our lateral systems and everything, so if we can lighten the mass and build a lot of concrete buildings, it's a good thing, right? Okay. Save material. So we can save, for this building, we could save 20 miles of concrete sidewalks, all right, or maybe a steel for 1,000 cars. A big deal. It's worth thinking about. The client for this project was really excited about this. In fact, he said, okay, we should get people to get water bottles from San Francisco, you know, because you get into the thing, we'll assemble it, it'll be a community effort, we'll bring the water bottles to site, and we'll, you know. So whoa, wait, it's a little bit more complicated than that. In the end, he sold the building and the site, and the client that bought it, okay, get this one, even with this plastic, they said, look, we can't, the supply is not fast enough. We can't get the supply to the site fast enough to build this building. And it's true, because we're stuck on this idea that we have all this material, but the way to get it to the site in a way that's controlled takes a process. It takes a will, right? And he just felt that there wasn't enough time for this thing to happen. So I don't know, we'll see. But what did happen is that we digitally mapped these long span slabs. We placed a camber in the system. We used post-tensioning to create these wonderful open spaces, free of beams, with a lot of light, and tight floor-to-floor heights, okay? So long span concrete, flat plates is something that's worth thinking about in our buildings, especially if you have multi-story buildings. And it's all about carbon, right? It's about reducing carbon. If you go to our website, there's actually if you have a Mac, unfortunately you can't run, I have a Mac and I can't run this program, but if you have a PC-based laptop or desktop, you can run this. It's free. This calculates the amount of carbon in materials that you use for your building, in the construction, and also what we call probabilistic seismic damage. So if you have a higher performing system like seismic isolation, the impact of carbon is going to be less over time when we look at a building over its life, right? Anyway, check it out. It's available, and it's something that also, when we design, we can do better at. So for instance, as our design gets refined from concept to all the way through construction administration, you can look at reducing carbon and then actually measuring carbon, measuring the amount of materials and the time it takes to build your building when you build it, right? So it all adds into that carbon calculation. And this program will do it for you. So what do we learn from this? And this is based on a study that Mark did when he was in our studio in San Francisco, and this building is going to start construction fairly soon. It's a residential building. It's not super tall. It faces the bay. Very, very important property and a very expensive building. So what we did is we looked at it, and in plan, it's pretty straightforward. It's a series of columns that march around the floor plate, and there's a cantilever on the outside edge, and then there's a central core. That's it. Everything works within it. Columns are carefully placed between the partition walls. You get these great column-free edges, and we have a flat plate, just like 350 Mission, the one that I showed you before. But now we're thinking, well, how do we do a better job of the post-tension system? How can we optimize, use those same principles on the horizontal plate that we did for the vertical building? And these are Mark's studies. And on the left side, this is what we do in all our buildings. And you look at it today. If we, in a post-tension floor plan, you'll find an orthogonal layout of cables within the structure that yields an efficient design. But the question is it the most efficient? So we looked at different ideas of how to lay out those rectilinear grids, and we found that we still couldn't really optimize it all that much until we get to the right one. Now look at what happens. it looks much more like an organic form or a flower, or it looks at, and guess what? It maps the actual force flow in the slab. So it places the cables exactly where we need them. So what we've been doing for all these years is okay, but maybe not the best way. And we know that when we use post-tension cables, we can move them in plan and in elevation, right? I mean, they're flexible, and we can, whether they're bonded or unbonded. Typically in the United States, we use unbonded tendons. And you can create these floor systems, and you still have to coordinate with mechanical and that sort of stuff. And you can find that you might reduce the amount of post-tensioning tendons in the slab systems by 25%. It's a big deal. Post-tensioning is expensive, and we do a lot of these types of buildings. So these are kind of incremental changes that we hope that will find their way into the main construction marketplace based on these principles. Okay, so I'm going to just say a few more things. Back to the city. Everything that you see in white is planned. This is in Guangzhou, China. So the plans are not insignificant, right? So you wonder whether or not we can have a great impact on cities. When we design cities and we think about materials, we think about transportation. And cities are loaded with data, right? I mean, the technology today with cell phones and other things, it goes without saying, data is everywhere, right? The question is, what do we do with data? So what if we thought of our cities like fields? I call it sensory fields. So fields that has data that we can use for our buildings, perhaps. Ground motions, like when the earthquake's coming. We know it happens pretty quickly, but we actually, in advance of that earthquake hitting our site, we know the speed that it's moving, we know the direction that it's moving in, and we know the amount of force that's coming. And perhaps our buildings could be tied to that knowledge. Wind is the same way. So how do we take the field and connect it to our buildings? Well, we do a lot of work with analysis. We know a lot about our buildings. We analyze them to death. We look at every single load case. We look at every direction. But what if we knew the direction and magnitude? And maybe our structure can respond only to that direction and magnitude. And maybe those analysis models are now tied into the actual live data that might come to that building during an event. And maybe we can do things like this, where we could elevate buildings, decouple buildings temporarily. Now, a few years ago, somebody would say, well, an electromagnetic field is something that's not possible because we had a big earthquake and the power goes down, there's no power for the magnets, and it's never going to work, right? Well, guess what? Guess what? Tesla and other companies have created a way to store energy, right? So this energy is now available. It can be available all the time. So these ideas maybe aren't so far off. Decoupling buildings temporarily from the ground. There's another idea. It's called, this one may not work either. I don't know. Let's see. Okay, it does work. I call it self-reflection. This is the same daughter from the Eiffel Tower. It's the same trip. We're in Berlin now. This is a carbon fiber ribbon bridge. It's a pedestrian bridge. And all the graduate student did was introduce air into the handrails, and it changed the characteristics of the bridge itself. So you wonder if we can actually control the movement of bridges, the movement of buildings in a temporary case where we call it a self-reflection. So we get movement that's starting, and then we have a reaction where we introduce something like air, or maybe some liquids into this building. And the point here is that now materials that were very high strength and very, very minimal could perhaps be used in our buildings and our bridges if we use this type of idea. Okay. So Self-reflection, joints that perhaps would rotate where others wouldn't. Maybe there's a way to control the friction in these joints so that some joints have a higher coefficient of friction than others. Maybe there's an idea that we take our buildings and we think about them as rheological systems. Systems where fluid is part of the idea. So in its basic sense, we build buildings that have structures that perhaps are made of steel, that have hollow sections. Today, what do? We fill them with concrete. So we make them stiffer by filling them with concrete. Years ago, we used to do things like fill them with water. But the idea might be that instead of just double wall systems like the one that's shown here, maybe the structure has multiple purposes. It resists load, but maybe it resists load in a very efficient way, and maybe these are conduits for other things, maybe liquids, maybe materials that change phase, right? So there's an external energy that's applied, and it takes a building that's otherwise very static, perhaps, into something that introduces a phase change. So the simplest sense might be a liquid to a solid, right? So if you were able to take, and you understood where the demand was the highest, maybe you take the very minimal structure and you change the characteristics within, and maybe you change it so that they're stiffer when needed, right? So liquid to a solid, temporarily. I don't know. It's a way to take the absolute minimal structure and perhaps change its characteristics over its life when it's needed. Planning of cities. You know, I think there's much more to this, and there's much more to offer from the engineering side that's been thought of than it has been thought of in the past. What you see in the blue in this diagram on the right are areas where you've gone below a target efficiency for use of your floor. So you know how we set a certain net area for use, right? If we drop below that target net area, let's say it's 80% for a building. We want 80% of the area to be usable. In this case, for those buildings in the areas in blue, we're under 80%. And why? Why are we under 80%? Maybe the structure's too big. Maybe we're using concrete. We should have used steel, right? So the structure's taking up space. Maybe the elevatoring is such that it's taking up too much space. You have too many elevators, right? But a lot of it's based on material and geometry. So you wonder, when you plan cities, shouldn't we be thinking about this? We shouldn't be just thinking about sun and shadow and transportation. We should be thinking about geometry, placement of buildings on sites, materials, efficiency. Efficiency is probably the most important things to our client, because that's what makes money, right? Usable space. So we've been developing these ideas that parametrically model cities interactively. So looking at form, building efficiency, carbon, solar, and structure, and maybe there are others, all at the same time. And you can weight these things. So you could say, well, my building efficiency is most important, so I'm going to strive toward the highest efficiency. Or the form of my building is the most important, and I'll put less weight on the other things. But this is a way to make planning perhaps a little bit to the next level in terms of how we think about our cities. So it's a progression, right? It's this path that great architects have set forth for us, and I think that when we think about these ideas in the future, maybe if we think about what if structures in the future could be designed for the basic sustained forces by using the material internally flowing in response to a transient loading, increasing in density in areas where necessary. What if the behavior was three-dimensional, considering the volume of the structure rather than just at its perimeter? And what if the behavior emerged from a central controlling force of a collective intelligence? Maybe structures would look different, right? It's another step of evolution of what these ideas might be. Okay, so there's a book. So, okay. So this thing just, yeah, 20% discount. Okay. I'm not here really to sell this book, but I just want to tell you guys there's a book. This book is in the second edition, so somebody must be reading it. I don't know. I wrote this book actually from a studio class, kind of like what we're doing today at Stanford. They don't have a school of architecture that's accredited. It's under the civil engineering program, but there are a lot of very bright people at Stanford. And this was a series of class notes from that Stanford class that's now been expanded. Anyway, it's up here if you guys want to take a look at it. It's a reference. It tries to take some of these ideas from the very basic all the way through these complicated things that we're talking about today. And there's a discount. There's a little flyer here that's maybe floating around. So as one of my partners in San Francisco said, look, like this book I guess is maybe, I don't know, I guess $40 or something. And he said, well, you can get a 20% discount. So for all, you can sell for $30, like everything you know is $30. Anyway, whatever. Okay, so that's out here if you guys want to take a look at this. Now, there's another book out here that's actually pretty good. This was just released. This is not just about tall buildings, but all types of buildings. It was published by Detail. And it's just a look at what we've been doing. And it's not what you think, okay? You think about SOM and tall buildings and commercial buildings. There's a ton of stuff that we've been doing, and I was showing you a bit of it today, that is not tall buildings, but based on some of these principles of nature and perhaps the environment. So back to the ground. You know, there are things that we do that work. They work. And, you know, in China, there's going to be a tall building. In fact, there is a tall building now sitting on this site. These are the caissons that are being hand dug. And they telescope down about 30 meters. And it's done, they're hand dug by a team. And typically it's a brother and sister, or a man and wife, a couple of brothers. The most important job is actually not digging the hole. It's the person at the top that makes sure that nothing's going to come down and hit the person inside the hole. And in some cases, getting air down inside the hole. So this idea of this collective, right? But it doesn't have to be so scientific always. And we need to think about what it means when we design our buildings and how these principles that are new work with principles that are very old, that work and make things safe. And think about how things grow and how that might impact our ideas about design. And this sort of very sort of fluid way of freehand sort of thinking about structures and form and what these simple sketches might lead to, right, in terms of design. And it could be one of the solutions. It doesn't have to be them all, right? And so these fluid forms that set yet the next step in the way we think of design. There are other ideas that could happen. This is for a 600-meter tall building in Bangkok that's under concept design right now. And you take them and refine them into something that hopefully will be beautiful and define architecture in a new way. So it's a work in progress. It's something that we think is really important, and I think we've got a great responsibility to do this. And you know, I think these things create something that's new. You know, there's a new architecture that comes from these ideas. And when I say architecture, I mean the collective architecture, the planning, the engineering, the construction. So that's what I have for you today. And how am I doing on time? Am I out of time? I'm okay. Okay, so if there are any questions, be happy to try to answer them. If we have a few minutes, I do have a little thing that maybe I could try to play for you that might inspire you. But in the meantime, I don't know if anyone has any questions. Be happy to try to answer them.
I have a question about timber buildings, because you said that carbon is very important in engineering today. So I know that SOM has already done some studies about very tall building in timber. Do you think that's something feasible?
The answer is absolutely yes. And we have an example of one here that's 7 stories tall, right? 7. And I think that the tower that you're talking about is a study, just so everybody knows, is a study that we did for a structure that would be made of wood, mostly wood, of the DeWitt Chestnut apartment building in Chicago. And that was a project that was done by Fawzer Khan and Bruce Graham. And that was also done in the 60s. And it's a concrete frame, it's a tubular frame. And I would argue it's maybe one of the most important buildings because it used concrete and it used this tubular frame, which set forth a structural system that's been used in many, many ways afterward. We did it in wood instead. We took that same frame and tried to design it out of wood. And it's about a 28-story building, something like that. A couple of things that we did in that project. It's not all wood. It's a combination of some concrete, but mostly wood. Okay, so what we did in that case is we had a shear wall building, concrete wall in the center to resist lateral loads. And then we had wood columns, we had wood floors, and we topped it with concrete. Because in the United States we have a pretty significant fire resisting requirement for our buildings. And because of the fire issue, I think that's what's restricting really most of these tall buildings going forward, because people are just worried about the rating mostly on the horizontals. The horizontals, if they were wood in a multi-story building. The large timber for columns and the CLT that we can use for the horizontals and the verticals, it's mostly the horizontals that have yet to be completely defined in terms of what the resistance is. And typically in the United States it's like 2 hours. 2 hours. But I think it's really worth thinking about in tall buildings, okay? So maybe some of you are studying this. I think you should push this and think about the fire rating. You know, charring of large timbers, it's all smart stuff because it self-heals, right? Self-heals and you get fire protection. It's a good solution. Now, think about the earthquake. So when you take your wood building, what are you going to do in the earthquake? Because wood, right? Wood is maybe not the best in the earthquake. So we got to solve that problem, but I think we can, and maybe it's by mixing materials. But I think it's a good idea. So if you're interested in it, you should keep pushing it. There's an engineer in Chicago. His name is Ben Johnson. He'd love to hear from you if you're interested. Send him an email. Ben Johnson. He's a guy that's been pushing it, and he's a good resource. Okay. All right.
Yeah, Mark, you've been talking about structure and architecture, so you know that in your field, obviously, but and you've been talking about the nature, like Darcy Thompson on growth and form, but you never submit this idea with other parameters like labor, environmental situation, solar situation. How can you distinct those parameters with the one on structure and architecture?
So you mentioned labor
of conditions, for example.
You mean to build? To
build. The situation where when you are in China is not the same one as in United States, for example.
Right. And then you mentioned
quality of material, the quality of the labor, the price of the labor.
Yes.
How do you mix all those conditions with the one you're talking about now?
Sure. Yeah, and that's a really good point. I mean, okay. So when we design these buildings, ultimately they have to be done well and they have to be safe, right? So you want to be sure that your risks aren't so high that the people that are building it can't do it. Now, you mentioned China. The argument about China is, in fact, the craftsmanship for construction itself in these, I'll say, major construction organizations that are largely state-run are very good. So buildings that we're building, like Jinmao, and some of those tall buildings, they have very, very good people on their workforce that understand construction. In fact, a lot of the ideas that I showed you actually are in the process of being done in China, or they've already been done in China. In fact, that tall building that I showed you with the steel structure, the diagrid structure is very complicated in elliptical form, built in Beijing. But we need to think about that and think about it carefully. I think that the problem with construction around the world, it is very, very slow to move in technology. I mean, look at the other forms of technology that we see and how quickly they move, whether it's telephones or cars or whatever it is. But the construction industry is very, very slow to move. I think it's a good challenge for all of us to really push that and see where we can go. And I think one of the ways we're doing it is getting closer to construction by the way we create documents. So, for instance, our design drawings now, I would argue, are getting closer to construction than they were in the past. So digitally, creating our drawings and giving them to the contractors so they can use those drawings directly, that's the goal, instead of being far away. Now, Mark, you mentioned solar, I thought. What are you thinking about that?
No, I was thinking of, but you answer with labor. There are many parameters on which are depending the drawings also. Solar energy. Yeah. We were talking a little bit about this at lunch today, because I think the studies, the track of studies that are being done at the university now are considering, more ideas of architecture and engineering as they relate to the environment, right? So solar is a very... Okay, what if, just for example, what if all those buildings that we do, what if the exterior wall systems were able to not just control the temperature inside the building and not just control things like glare, but also were there to actually generate power? So all those walls that we're using are, in my view, over time have been, there's a wasted opportunity. It's a wasted opportunity. So if you could be the next person to think about how we create those exterior systems that are so much smarter than they are today. We're looking at things like electrochromatic glass, changing the characteristics interactively of the glass and the environment is a step in the right direction. The other thing that I think is around the same line as what you're talking about is elevatoring. Elevatoring in our buildings is about the most efficient, archaic, almost nothing's happened since when Otis discovered the elevator, except for speed. Think about it. And it takes up a huge amount of space in our buildings, and it all gets into that big thing that we were talking about with terms of carbon and the amount of materials that we use. Imagine if we could use half the amount of area for our elevators. And how do you move people vertically? I don't know. Maybe there's a movement vertically and there's an offset that happens that allows a single shaft to have multiple purposes. But these are the things in terms of architecture and invention that we should really be pushing for. It's not just what the building looks like, but what can we do to make these things more efficient, right? So anyway, there's a good question. It's all sort of tied together, and I think there's a lot of work that we can do for this. Anybody else have some thoughts? Yeah, I don't know if we're going to be able to do this or not. You guys. Anyway, the movie I was going to show you, I'll just describe it briefly, is the same daughter that was with me with the popsicle stick model was at really the farthest point north on the planet.
in the Arctic not so long ago. And what's interesting about this place is that what she saw really was change. There really are things happening there. So maybe I'll leave you with the thought that these places still exist, but they're so fragile. And the point here is that with this fragility that we have, we need to think about what we're doing in terms of our designs today. And it can be very, very small. It could be a part of a building that matters, right? It doesn't have to be a big 100-story building. So that's the message, I guess, is that these things really do matter, and it's worth thinking about it that way. So maybe I'll just leave you with that thought.
Marc, thank you very much. Maybe on peut le remercier, monsieur.
Thank you.